Okay, in the last class, we looked at the matrix representations for the symmetry operations of the ammonia molecule and derived the character table for the point group C3, to which the ammonia molecule belongs. So we've seen that in the point group C3, the coordinates x and y are degenerate each other, so depend each other. They depend on each other and belong to the double degenerate symmetry type E. Now, the character table is a very convenient way to see that, well, a particular coordinate or a particular mathematical function is degenerate. But is it actually possible to also understand that and derive that? So, for instance, is it possible to understand that the px and the py orbitals of the nitrogen atoms in the ammonia molecule are double degenerate? If that is the case, then there must be an application of a symmetry operation that interconverts the two orbitals. Okay, so this is a general rule. When a symmetry operation is interconvert two orbitals, then they must be degenerate in the respective point group. So now, when you look at these two orbitals here, then you see that they stand perpendicular to each other. But there's a C3 rotational axis in the molecule that rotates around 120 degrees. So for that reason, it's not straightforward to see the degeneracy. It's not straightforward to see that there is actually a symmetry operation that interconverts these two orbitals. However, it can be seen with a little trick that I would like to show you now. To apply that trick, we need to first reorient, or we should first reorient the ammonia molecules. So we look at it now from the bird's perspective. And we know that the ammonia molecule contains three vertical mirror planes. This one here that goes through this NH bond, this one here that goes through that NH bond, and the third one goes through this NH bond here. So now we can define the coordinate system so that it is rotated by 45 degrees relative to one of the NH bonds, and therefore also 45 degrees relative to one of the mirror planes, in this case, this mirror plane. Okay, we can do this because we can arbitrarily define our coordinate system, and we can choose our coordinate system in the way we want. So now, if we define this to be the x-axis and this to be the y-axis, and of course the x and the y-axis have to stand perpendicular to each other, then the px and the py orbitals would need to be oriented along the x and the y-axis respectively. So our px orbital would be oriented here, and our py orbital would be oriented here. So can we now see that there is a symmetry element that interconverts the two orbitals? We can see that this mirror plane actually does this. Yeah. Because if we mirror our orbitals here at this mirror plane, okay, then this slope here is being mirrored into this position here. Okay. This slope here is mirrored into this position. This slope here is mirrored into that position. And this slope here is mirrored into this position. Okay. So we have converted the px orbital into the position of the py orbital, and we have converted the py orbital into the position of the px orbital. Okay, so in this way we have proven that these two orbitals are doubly degenerate in the point group C3b. You see, and it was not straightforward. In order to prove this, it's much easier to look into the character table, and therefore the character tables are of such a great use in chemistry. Okay, now we have finished our chapter on symmetry. So let us now move over to the next chapter, in which we apply symmetry to molecular orbital theory. So you have probably all heard about molecular orbital theory, but now we will discuss molecular orbital theory from the perspective of symmetry, and apply symmetry in order to construct molecular orbitals and molecular orbital diagrams. And you will see that with the help of the symmetry, we can much more easily understand molecular orbitals. We can much more easily construct molecular orbital diagrams, especially when the molecules get more complex. For very simple molecules, we do not necessarily need to apply symmetry, but for more complex molecules, the application of symmetry in group theory to molecular orbital theory is very, very helpful. So as an introduction to molecular orbital theory, let us first briefly review the axioms of molecular orbital theory. So like any theory, molecular orbital theory makes a few assumptions, and making these assumptions can then explain the bonding. So molecular orbital theory was developed in particular for covalent bonding. But as you will see, it can also make statements about ionic bonding and even metallic bonding, but this will not be covered in this course. I cover that in my other course about solid state chemistry. So let us briefly discuss the two axioms on which molecular orbital theory is based. So the first axiom is the so-called Born-Oppenheimer approximation. It says that the nuclei are much more massive than the electrons, and because of that, the nuclei are nearly fixed with respect to electron motion. So the second axiom says that molecular orbitals can be described as the linear combination of atomic orbitals. So a linear combination means a vectorial addition. So as we construct molecular orbitals, we vectorially add atomic orbitals together. So this can be mathematically described the following for two atomic orbitals that are forming molecular orbital. So like the atomic orbitals, the molecular orbitals can be described by a wave function, psi. We can call that wave function psi AB if the molecular orbital is formed from two atomic orbitals A and B belong to the atoms A and B. So psi AB is the vectorial addition or the vectorial subtraction of the two atomic orbitals psi A and psi B, whereby psi A and psi B have coefficients Ca and Cb that determine the degree to which the atomic orbitals contribute to the molecular orbital. Okay? So a high coefficient means a high contribution to the molecular orbital. A lower coefficient means a low contribution to the molecular orbital. So then you see here a factor n in front of this term. So this is the so-called normalization factor. You know that normalization factor ordered from atomic theory. So in atomic theory, the normalization factor associated with an orbital guarantees that the integral over the square function of the square of the wave function of the atomic orbital is equal to 1. This way we ensure that the probability to find the electron somewhere in the respective orbital is 100%. And the same we do also molecular orbital theory, that this normalization factor is chosen so that the probability to find the electron somewhere in this molecular orbital is 100%. So in molecular orbital theory, the molecular orbitals must always be the number of atomic orbitals. And when we have two atomic orbitals that we combine, we must therefore get two molecular orbitals. Okay? One refers to the vectorial addition of the two atomic orbitals, and one refers to the vectorial subtraction of the two atomic orbitals. So now you could ask, well, what's the thought behind that process of adding up atomic orbitals to molecular orbitals or subtracting them? And in order to understand that, it helps that, well, the wave functions describe the electrons as waves. And as we bring atoms together to make a bond in between them, these waves start to overlap. Okay? So when they start to overlap, they start to interfere. And now there can be two types of interferences. There can be constructive interference, and that constructive interference relates to the vectorial addition of the two atomic orbitals. And there can be a destructive interference, and that destructive interference relates to the vectorial subtraction of the two atomic orbitals. Okay? So the orbital that results from the vectorial addition will actually have an electron density maximum between the nucleus, the two nuclei, okay? And therefore we can say that that electron density is shared between the two nuclei, and that relates directly to the concept of covalent bonding, in which we assume that one or more electrons are being shared between two atoms. Whereas the interbonding molecular orbital is interbonding because there is a node in between the two nuclei where the electron density is 0. So a bonding situation occurs when more electrons are in the bonding state rather than the interbonding state, and that defines the bond order. So let us understand this in more detail. Let's just assume we have two hydrogen atoms, and the two hydrogen atoms have a 1s orbital each, and we have one electron in these 1s orbitals. Okay. So now we have basically two possibilities. The first possibility is that, well, the algebraic sign of the two wave functions of the two 1s orbitals is positive or the same. And the other possibility is that, well, the algebraic signs of the two wave functions are different, and that's indicated here by different colors. So now as we form a bond between these two atoms, we bring these atoms closer together. Okay, so now let's do this. Okay, and you see as we do this for the two 1s orbitals that have the same algebraic sign, we are creating here an electron density maximum in between the two nuclei, which refers to, well, covalent bonding situation. And that type of interaction refers to the vectorial addition of the two 1s orbitals. Okay, and now we have also the other possibility. So now as we bring the two 1s orbitals opposite algebraic sign together, okay, because of destructive interference, we are forming a node in between these two orbitals. So that refers to an interbonding situation, and the vectorial subtraction of the two 1s orbitals from each other. Okay, so the bonding orbital will have lower energy than the interbonding orbital. We can understand this from the concept of nodes in orbitals, and in waves generally referring to energy levels. But generally, the fewer nodes a wave has, the lower its energy. So this molecular orbital doesn't have any node, while this molecular orbital here has a node in between where it actually changed its algebraic sign. For that reason, this orbital has a higher energy than this orbital. Okay, now we can define the bond order as the number of electrons in the bonding MOs minus the number of electrons in the interbonding MOs over 2. So now if we construct an H2 molecule from 2 hydrogen atoms, what would that mean in terms of bond order? Well, for the H2 molecule, the bond order would be 2 minus 0 over 2 is equal to 1, because we could fill both electrons coming from the hydrogen atoms into the bonding molecular orbit. Okay, so the bond order would be 1, representing one single bond in between the two hydrogen atoms. Now we can think of, well, what if we had an H2 plus ion? What would be the bond order then? So in this case, we would only have one electron. So that electron could be filled in the bonding molecular orbital of lower energy. So we would have no electron in the interbonding orbital, and the bond order would be 1 minus 0 over 2 is equal to 1/2. Then the bond order would be smaller in comparison to the H2, but it was still larger than 0. So we would conclude from this that the bond in the H2 plus ion would be weaker, but there would still be bonding forces there, and we would expect that we would be able to observe such an H2 plus ion experimentally, and indeed such H2 plus ions have been observed experimentally. So we can further ask, well, if we have an H2 minus ion, then we would have 3 electrons available. So now 2 of them could still go into the bonding molecular orbital that has a lower energy, but the third one, because of the Pauli principle, which applies to molecular orbital theory as it applies to atomic theory, would need to be filled into the interbonding orbital. So now we do not only have bonding electrons, but also have interbonding electrons. But what would be the bond order? Well, in this case, it would be 2 minus 1 over 2 is also equal to 1/2. So that would mean that we again have a weaker bonding situation compared to the H2 molecule, but we would predict that an H2 minus molecule could still be stable because we have more stabilized bonding electrons than we have destabilized interbonding electrons. And indeed, one can observe the H2 minus ion experimentally also. So last but not least, well, would an H2 2- ion be stable? So now we have 4 electrons, and that must mean that we need to fill both the bonding as well as the interbonding molecular orbital completely. Now we have as many bonding as we have interbonding electrons. And now the bond order is 2 minus 2 over 2 is equal to 0. So that means that no bonding should exist between the H- ions, and we would expect that an H2 2- ion would not be stable, and indeed such an ion has thus far not been observed. So you can see that molecular orbital theory can help you to understand why certain molecules exist and why they do not exist, and it can also predict the stability of molecules. So whenever the bond order is larger than 0, then there's a potential for this molecule to exist. When the bond order is equal to 0, then this respective molecule should not exist. You can also see that molecular orbital theory does not require electron pairs to form a bond. It's sufficient when you have only one electron being shared to form a bond. So this is different in comparison to the simple valence bond picture and simple Lewis dot structures, where you always need electron pairs to form a covalent bond. According to molecular orbital theory, that's not really necessary. There can be also other cases. For instance, there can only be one electron being shared by 2 or even more atoms. Okay, now since we have understood the molecular orbitals of the H2 molecules, we can construct what is called a molecular orbital diagram. So in a molecular orbital diagram, we first plot the atomic orbitals that we use, and these are typically the valence orbitals of the respective atoms, according to energy. And we indicate the energy of the orbitals by an arrow that's pointing up, and we write a capital letter E on top of it. So now in the case of the valence orbitals of the hydrogen atoms, we know that they both have an energy of minus 13.6 electron volts, and we can write that value next to these orbitals if we know that value. Okay, so now in the next step, we write the bonding and the interbonding molecular orbital according to energy. So these energies can be quantum mechanically calculated, but as part of this course, we will not do any exact quantum mechanical calculation. We will construct what is called qualitative MO diagrams, in which we just estimate the interactions between the atomic orbitals and only estimate qualitatively the energies of the respective orbitals. So what we can say based on that is that, well, the bonding molecular orbital should certainly be lower in energy than the 2 valence orbitals, and the interbonding molecular orbital should be higher in energy than the atomic orbitals, and the distance of the interbonding molecular orbital from the valence orbital should be approximately the same as the energetic distance of the bonding molecular orbital from the valence orbitals. So in molecular orbital diagrams, you always connect the molecular orbitals with the atomic orbitals from which they have been constructed from with dotted lines. You see that here. All right. So now, in this case, the bond that we are forming is a sigma bond. Therefore, we can call this orbital the sigma orbital, and this orbital the sigma star orbital. You indicate by the star that this orbital is interbonded. Okay, so now we have to fill in the electrons. So there's one electron in each one is orbital. We can write them both as arrows into the molecular orbitals. To be exactly accurate, we should choose the spins of the two electrons to be opposite, because spin reversal is quantum mechanically forbidden. And in the next step, we have to write the two electrons here spin paired in the bonding molecular orbital. However, you will also find in literature that they are written both spin up. This is a minor inaccuracy, but it's usually not being seen as a mistake, and I also won't blame you for that in an exam. I just do it here as accurately as possible. Okay, so now we have filled our molecular orbitals with all the electrons, and that means that we are basically finished with our molecular orbital diagram. Okay, so now the H2 molecule is of course extremely simple, and the molecular orbital diagram of the H2 molecule is also extremely simple. But more complex molecules require more considerations when you construct molecular orbital diagrams, and therefore in the next step we will look in more detail at the factors that influence the degree of covalent interaction and how that influences the way we construct molecular orbital diagrams. All right. So there are three factors that influence the covalent interaction. The first one is symmetry. So only when the molecular orbitals are correctly oriented to each other, then there can be a covalent interaction between them, and we can form molecular orbitals. Okay? In fact, the orbitals must be oriented so that the bonding and the interbonding actions between them do not cancel out. If that's not the case, then there can be a bonding interaction between them. And bonding and interbonding always refers to constructive and destructive interference. You can also say when the constructive and the destructive interferences do not cancel out, then there's a bonding interaction. So secondly, there's the overlap criterion. And that overlap criterion says basically that the stronger the orbitals overlap, provided they have the correct symmetry, then the stronger the covalent interaction. And lastly, there's the energy criterion, which says that the closer the orbitals are in energy, the stronger the covalent interaction. We can understand this the following way when you consider that the orbitals are waves, and energy is correlated to wavelength, and two waves that have similar energy will just interfere more strongly with each other than waves that have very different wavelengths in energy. Okay, so now let us look at these criteria step by step in more detail. And let's start with the one that's probably most simple to understand, and that's the so-called overlap criterion. So for the overlap criterion, there are a number of rules to consider. So the first rule says that the smaller the distance between the atoms, the larger the orbital overlap, and the larger the covalent interaction. Of course, again, provided the symmetry is right. So that's fairly straightforward to understand. As we bring the orbitals closer together, they will overlap more, and the more they overlap, the more strongly they will interfere with each other. Okay, so that has now the consequence a consequence when you construct molecular orbital diagrams. Okay, so if you have only a weak overlap, then that means, well, the energies of the bonding and the interbonding molecular orbitals are not very far from each other. Okay, so the energy difference is relatively small, and the energy of the bonding and the interbonding molecular orbitals are also relatively close to the atomic orbitals. Okay, but if there's a small distance, there's strong overlap, the energy split becomes greater. Okay, and you also have to write it like this in a molecular orbital diagram. Okay, so for that reason, this molecular orbital here is strongly bonding, and this one here is strongly interbonding. While in this case, this orbital here will only be weakly bonding, and this one will be weakly interbonding. Okay, as I said before, here we will have a large delta E. Here we will have a small delta E. So what is our second rule? Well, our second rule says that a large diffuse orbital tends to overlap better with another orbital when this orbital is also a large diffuse orbital. Okay? When we have a small or little diffuse orbital, then it tends to interact more strongly with another little diffuse orbital. Okay? So large gives good overlap and strong interaction. Small gives also good overlap and strong interaction. But last but not least, when we try to interact a very large diffuse orbital with very small compact orbital, then they don't interact very well because they don't overlap very well. In particular, when you look at the large orbital, you see that only a very small fraction of its volume can actually overlap with a small orbital, and that leads to weak interactions. Okay, so again, weak interaction leads to a weakly bonding and a weakly interbonding molecular orbital in the molecular orbital diagram. Okay, the energy difference between the bonding and the interbonding molecular orbital tends to be small, whereas in the other two cases, we have strongly bonding and strongly interbonding molecular orbitals. The energy tends to be large. The same also for this case here. We have strongly interbonding molecular orbitals, and the distance, energy distance between the bonding and the interbonding molecular orbital tends to be large. All right. So what is rule number 3? Rule number 3 says that there's a tendency that orbitals that overlap in sigma fashion interact more strongly than orbitals that overlap in pi fashion. So that is immediately obvious when we actually inspect orbital overlap. So for instance, here we have two p orbitals that overlap on the bond axis. Okay, whereas here they are overlapping perpendicular to the bond axis. We can easily see that when the orbitals are oriented this way, then they interact in sigma fashion, and well, there's a strong orbital overlap between them. Whereas when they are oriented perpendicular to that, they can still interact covalently. In this case, they interact covalently in pi fashion, but because of the less favorable orientation, orbital overlap is not as strong. And therefore, the covalent interaction is weaker. Again, you have to consider that when you construct the molecular orbital diagram. Okay? So again, the sigma interaction tends to produce strongly bonding and strongly interbonding molecular orbitals with a large delta E in between them. When you construct a pi bond, then you will have relatively weakly bonding and relatively weakly interbonding molecular orbitals with a relatively small delta E in between them. Okay, so this was the overlap criterion. Let us now move over to the energy criterion. So as I said before, the more close the orbitals are in energy, the more strongly they covalently interact. So the ideal case is when the energies of the two orbitals are exactly the same. They're actually only precisely exactly the same when two same orbitals of the two same atoms overlap. So for instance, we have two atoms A, which are of the same type, and we have two orbitals of the same type also. So for instance, A could be oxygen, yeah, and we would consider the interaction of the two 2s orbitals between oxygen. Then the energy of these orbitals would really be exactly the same. And that would lead to bonding molecular armor in an interbonding molecular armor in which the covalent interactions are being maximized. Okay? So in this case, the electron density maximum of the bonding molecular orbital lies exactly in between the two atoms A. Therefore, we can say we really have an exactly covalent bond, which has no polarity whatsoever. So the energy distance between the bonding molecular orbital and the atomic orbital is approximately the same as the energy distance between the interbonding molecular orbital and the atomic orbital. Okay, now if both partners have one electron, then both electrons would go into the bonding molecular orbital, and these two electrons would be exactly shared between these two atoms A, producing a completely covalent bond. So now let's look at the case in which the orbitals of the atoms of two different atoms A and B are somewhat different, as shown here. So now, also in this case, you can form a bonding molecular orbital and an interbonding molecular orbital. But now you see that the bonding molecular orbital is energetically more closely at the atomic orbital of the lower energy, and the interbonding orbital is energetically more close to the atomic orbital of the higher energy. In addition to that, this molecular orbital here is located primarily at atom B, while this interbonding molecular orbital here is located primarily at atom A. So now what consequence does that have for the bond? Well, first of all, you see that the energy difference between the atomic orbital and the molecular orbital, which is closer to it, is smaller in comparison to this case. Okay. Secondly, you see that when you fill in the electrons from the atomic orbitals into the molecular orbitals, that the electrons are now not completely equally shared in between the atoms A anymore, because that molecular orbital here is localized primarily at B, not completely at B, primarily at B, and therefore we will have a covalent bond which is polarized toward B. Okay. Note that if we had an interbonding electron also, then this would be here in this interbonding molecular orbital, and that interbonding electron would then be primarily localized A because the interbonding orbital is primarily localized at A. Okay. Now, in this case, that's not the case. We have only bonding electrons, and these bonding electrons will make a bond which is polar and which is polarized toward B. Okay. Now, last but not least, let us assume that the atomic orbital energies are different, but now they are much different. So we can still form a bonding molecular orbital and an interbonding molecular orbital. But now the bonding molecular orbital will be energetically very close to atomic orbital of B, and it will also be localized almost exclusively at B. Whereas the interbonding molecular orbital will be energetically very close to to A, yeah, and it will also be localized almost exclusively at atom A. So now if we fill in our electrons, and we assume again that there are two, into the molecular orbitals, we can fill the bonding molecular orbitals. But now you have to consider that this molecular orbital is actually almost exclusively located at atom B. So in this case, we will therefore have an ionic bond, okay? Because that electron pair here is localized practically completely at atom B. Okay, so in fact, we have actually performed a redox reaction in which we transferred this electron here from atom A to atom B. And now from that, you can understand that molecular orbital theory, while designed for covalent bonding, can also make statements about ionic bonding. From that, you can also see that while a completely covalent bond is being possible, in which the electrons are being shared exactly between the two atoms A, a 100% ionic bond is not possible because a completely ionic bond would require that the energy difference between the two orbitals A and B is infinitely large. But in fact, the energy difference is almost always finite, and because of that, there's always at least some degree of electron sharing between the atoms A and B. And there's always at least a small degree of ionic covalent bonding possible. Okay. Now, when you have a covalent bond formed this way, as we just described it, between two atoms A and B, and these atoms have different electronegativity, then that means that the bonding electrons are always located at the more electronegative atom. However, if they are interbonding electrons, then they are located at the electropositive atom. For instance, if we had in this case not two electrons but three, the third one would need to go into the interbonding molecular orbital, and that electron would then be localized almost exclusively at A. Okay, so we have now discussed the energy criterion. Let us finally discuss also the symmetry criterion. Okay? So we said previously that molecular orbitals can interact when the bonding and the interbonding interactions do not cancel out. If they do not cancel out, they have right symmetry, and if they cancel out, they have wrong symmetry. So here's an example that shall illustrate this. So we have here our H2O molecule, and we ask, well, is it possible to form molecular orbitals from the 1s orbitals of the hydrogen and the 2pz orbital of the oxygen? Okay. If that was possible, then the bonding and the interbonding interactions between the orbitals wouldn't cancel out. That means that the constructive and the destructive interferences would not cancel out. So you see here again the algebraic signs of the wave function indicated by color. And now you see that, well, you will have both constructive and destructive interferences. But these constructive interferences will be stronger than the destructive interferences. And that is because here this lobe of the 2pz orbital, which is the same algebraic sign as the 1s orbitals, will be closer to the 1s orbitals than the lobe here, which has the opposite algebraic sign. Therefore, the positive interferences will be stronger than the negative interferences, and therefore the bonding interactions will be stronger than the interbonding interaction, therefore they will not cancel out. From that, you can now conclude that it will be possible to construct molecular orbitals from that combination. Yeah? So we can also ask the same question for other orbital combinations. So for example, can the 2px interact with the 1s orbitals? So now you see that is also possible, but only if we choose the algebraic sign of the two 1s orbitals differently. Okay? Then this orange lobe can constructively interfere with this 1s orbital, and this blue lobe here can constructively interfere with this 1s orbital. Okay, so again, yes, bonding interactions can result when the orbitals are combined as depicted below. Okay, we can choose the algebraic signs of our orbitals so that the bonding, the interbonding interactions do not cancel out. Right? If you have chosen the algebraic signs to be the same, you would see that we would have constructive interference here, but destructive interference here, and they would be exactly the same because the degree of orbital overlap here and here would be exactly the same. Okay. Okay. So I see we're running a little bit out of time. Maybe we can add this example at the very end. So the oxygen atom also has a 2s orbital, and now we can see that we very easily can create constructive interference because a 2s orbital can overlap with the 1s orbital simply when we choose the algebraic sign of the three orbitals to be the same. So can we combine the 1s and the 2 orbitals in a way that leads to a bonding interaction? The answer is yes. We can do this, and therefore there will be MOs from the 1s and the 2s orbital. All right, so just to make this complete, although we are already a little bit over the time, let me also discuss the interaction of the 2py orbitals with the 1s orbitals. Okay, so the 2py points into the board plane. So one lobe points to the front and the other lobe points to the back. So now you can see that no matter how we choose the algebraic signs of our 1s orbital, the bonding interactions always cancel out. Okay, you can see this more easily when we actually choose the coordinate system differently. So now we are looking at the H2O molecule from the bird's perspective. So this is our x-axis, and this is our y-axis here. And now you can see more clearly that the bonding interactions always cancel out. Okay, so we have, for instance, constructive interference here, but it's exactly the same as the destructive interference here. And this constructive interference here is exactly the same as this destructive interference here. It doesn't have if we change the algebraic signs of our 1s orbitals. So in this case, we would have constructive interferences here and destructive interference over there, and constructive interferences here, but equally strong destructive interferences over here. So no matter what we do, the bonding and the interbonding interactions always cancel out. And therefore, the combination of the 2py and the 1s orbitals will not result in molecular orbits. Okay, let's stop at this point. And I just stopped the recording.